Welcome back to Mr. Hassan's Maths channel. I'm answering now a question from Mechanics 1, M1, June 2015, the GCE version, about connected particles and pulleys and inclined planes. Now, two particles P and Q have mass 4 kilograms and 0.5 kilograms respectively. Okay, so let me just start putting everything in here. So P has a mass of 4 kilograms. So you can say its weight will be 4g kilograms, 4g newtons, sorry. So that's 4g newtons, that's its weight. And Q has a mass of 0.5 kilograms, so its weight will be 0.5 g newtons, where g is 9.8. Okay, that's newtons. Okay, now let's put it in. Why not? All right. So particle P is held at rest on a fixed rough plane which is inclined to the horizontal at an angle alpha. So that angle alpha, where tan alpha is equal to 4/3. So the tangent of alpha is equal to 4/3. So let me just draw a right angle triangle. Okay, now supposing that angle here is alpha, that's a right angle. The tan of alpha is 4/3, as it told us. So that means the opposite is 4 and the adjacent is 3. That means the hypotenuse is going to be 5. 4, 3, 4, 5 triangle, okay, by Pythagoras' theorem. Now, that would mean that the sine of alpha, which we're going to obviously have to use when we're resolving the forces, is going to be opposite of a hypotenuse, which is 4/5. And the cosine of alpha is going to be adjacent of a hypotenuse, which is 3/5. We're going to have to use these, so that's why I'm writing this down. The coefficient of friction between P and the plane is 0.5, so the coefficient of friction is 0.5. And the string lies along the plane and passes over a small, smooth, light pulley, which is fixed at the top of the plane. Particle Q hangs freely. Okay, so of course you've got the tension in this string, which is the same all the way through the string because it's the same string and it's a light, inextensible string. The string lies in the vertical plane, which contains the pulley and the line of greater slope of the inclined plane. Okay, so basically the length you see is what it is here. It's not like some 3D type of diagram. Particle P is released from rest with the string taut and it slides down the plane. Okay, because there's friction involved. As this is sliding down the plane, so we can say that it's going to start moving down the plane this way. It's going to go like this. That means the friction is going to be acting opposing the motion. Always friction opposes the motion or the tendency to move. And as it's sliding down the plane, the friction has reached its maximum value. So I'll put Fm, means the limiting value, the maximum value of friction. Okay. Particle P is released, rest, and slides down the plane. Then it says, given that Q has not hit the pulley, find the tension in the string during this motion. Okay, so we're going to find what the tension is. All right, so we know that it's accelerating this way, and that's going up this way. Okay, let's take a snapshot of this and move it down there so that I can see what's happening. So I'll just do that and come back. Okay, so now I've taken a snapshot of what we had up there so we can see what we're doing when writing out the equations of motion. So there's a few more things actually I was supposed to put in, like that's the reaction force. Okay, there's always a reaction force when something is in contact with the surface. And the other thing we need to put in here is we need to resolve parallel and perpendicular to the plane. Okay, so this angle here is alpha. So as we're going, this one is resolved going into the angle, perpendicular to the plane. This is going to be 4g times cosine of alpha newtons. And this will be 4g times the sine of alpha newtons, because it's resolved away from the force, okay, away from the angle. The force, when you resolve, you have to move away from the angle. When you move into the angle, it's cosine, away from the angle, sine. That's 90 degrees there. So what we can do here is we can consider P, consider the particle P, and let's resolve perpendicular to the plane. Then we can find what R is. So we know that it's not accelerating in this direction at all. So we can say that it's in equilibrium in that particular direction. So r is equal to 4g times cosine of alpha. Therefore, r is equal to 4g times, we said the cosine of alpha is 3/5. So r is equal to 12g over 5 newtons. Okay. And we also know that the maximum value of friction, I'll just write that over here, the maximum value of friction is given by mu times r. So mu is 0.5, so that's like a half times 12g over 5. So that gives you 6g over 5 newtons. Okay, so we now have the value of friction, which is 6g over 5 newtons, and we have the value of r. So now let's resolve the forces parallel to the plane. Now it's going down the plane, so I'll take down as positive. So what we can say here is 4g times sine alpha minus the tension minus the friction, maximum friction, is equal to ma, and the mass is 4, so it's 4 times a. Don't make the mistake of writing 4g for the mass. 4g is the weight, not the mass. This, what we're using here is F equals ma. Okay, the resultant force is mass times acceleration. So that's a mass times acceleration, not the weight times acceleration. So don't make the mistake of writing 4g times a. It's 4a. Okay, so now we know sine theta is 4/5. So you have 4g times 4/5 minus the tension, which we don't know, minus the maximum friction, which we just worked out up there, which is 6g over 5 newtons. 6g over 5 is equal to 4a. Okay, so that will give me 4g times 4/5, that's 16g over 5. 16g over 5 minus 6g over 5. So you've got 16g over 5, let's do it step by step. Minus 6g over 5, oops, 6g over 5. (6g over 5) minus the tension, which we don't know, is equal to 4a. Okay, so we're getting somewhere now. 16g over 5 minus 6g over 5. Well, I'm going to just continue down here, although you would have to go to the next page really. So 16g over 5 minus 6g over 5 is 10g over 5, which is 2g. So 2g minus t equals 4a. So that's one equation. Now I'm going to just bring the diagram down. Oh, I've just added some things to it, haven't I? Whoops. Okay, I'll just look at it from up there. So now we want to resolve now. I'm going to look at, I'll do it over here. I'll just show that over the steps over here. I'm looking at Q now. Okay, for particle Q, it's going to be moving up. All right, so we can say T minus a half G equals MA, which is 0.5 or half A. Just keep it as a fraction for now. Equals a half A. Okay, that's resolving up. That's again using F equals MA. This is going up, so T minus 0.5G equals a half A. So that's like my second equation. So now I can use these two equations and solve simultaneously. So T minus a half G equals a half A. That's my second equation, and we're asked to find the acceleration. No, the tension in the string. Okay, if you want to find the tension in the string, then we can make the A is the same, and then we can find that, or we could find the acceleration first if you want, and then work out what the tension is. But let's find the tension in the string, as we're asked to find that. So what we could do is we can make the accelerations the same. So for example, I can multiply this by a half times 8 gives me 4. So this will become, multiply this whole thing by 8, I'll have 4a, and this will be minus 4g, and this will be 8t. Just multiply by 8, multiply by 8, multiply by 8. Now I have equation 3, and if I take equation 1 and 3, and I do 3 minus 1, if I do 3 minus 1, I'll have 8t minus minus t, which is 9 times t, minus 4g minus 2g, which is minus 6g. okay, is equal to 0, because 4a minus 4a was 0. We wanted to eliminate the a's. So we've got 9t, 9 times t is equal to 6g. So t is going to be 6g over 9 newtons, which you simplify that to divide by 3, 2/3 times g newtons. And that's the value of t. Okay, you can write your answer in this form. You can write your answer by writing 2/3 times 9.8 if you wish. Okay, so you can say 9.8 times 2 divided by 3 gives you, you could write your answer as 6.5 if you wish. Or you could also write your answer as 6.53 newtons. So all of these answers are acceptable. Okay, let's just check if it tells you to get it in a particular way. It doesn't tell you how to write it 2 decimal places or whatever. So the reason why they're all acceptable is because we use g in our calculations, and we have to use g as 9.8. When we're asked to use g, okay, we have to use it in M1 as 9.8. So that's already 2 significant figures. Therefore, our answer can be written to 2 significant figures. In general, we would answer to 3SF. So this is like the exact value. This is like 2 significant figures, and this is like 3 significant figures. And the examiners will accept all 3 of those. This is acceptable because g is to 2SF. So if we use something to 2SF, then we can keep 2SF accuracy for the rest of the question as well. Okay, as long as you use g. Otherwise, normally it will be in the exact form or to 3SF if g wasn't involved in this question. Okay, so t is equal to 2 over 3g. I like to keep it in exact, so I'll keep it in that way. Now, okay, now for part B, for question number 8. Here we have to find the magnitude of the resultant force exerted by the string on the pulley. So we know that there's a tension pulling down on the pulley this way, and the tension is the same in both parts of the string. Okay, if we're just considering the pulley now, if you look at the pulley alone, there's going to be, of course, a tension pulling down on the pulley. Okay, because this thing is going down, so that tension that's pulling this up is also pulling down on the pulley. The same thing here. Okay, but we're considering only the pulley now. Forget everything else. Forget all the other forces. I'm not worried about those forces. I'm just worried about the pulley now. Okay, now these 2 tensions are the same. They're both equal to the same value, which was 2/3 of g newtons. Okay, so there's a number of ways of dealing with this question, but by far the simplest way is to consider that the resultant force of these 2 is going to act exactly halfway between them. Exactly halfway. The angle here is going to be the same as the angle there, because these 2 tensions are the same. So that's the resultant force. That's what we have to find the magnitude of. Now there's a number of ways of doing that. Okay, but the easiest way of doing it, I'll go through that first, is if you just think about a line going along here, which is perpendicular to the reaction force, then you can think of, if I wanted to resolve this tension in the direction of the resultant force, I'm gonna, if you think this is like 90 degrees, if I want to resolve it in this direction, it's going to be t times cosine of this angle. And the same with this will be t times the cosine of this angle here. Alright, so we got to think about, what is this angle here? Well, if you think about what we had in the beginning, we had something like this. No, we didn't. We had something like this. Okay, this is alpha. Get my pop pen back. This is alpha. This is 90 degrees. So this must be 90 minus alpha. So let's work out what alpha is. We know that alpha is going to be the inverse tan of 4/3. So let's work out what the inverse tan of 4/3 is going to be. Whoops, why did I close it? The inverse tan of 4/3. So I'll press inverse tan of 4/3. I'll keep it in degrees. Yep, it's in degrees. That gives us 53.1 degrees. So this is 53.1 degrees. So this angle is going to be 90 minus that. So it's 90 minus 53.1, which is 36.869. So this is 36.869 ... degrees. That's the angle there. Okay, so the angle we need is a half of that. So let's take this and divide it by 2. That gives us 18.435. 18.435. So this angle here is 18.435. Okay, and so is this angle. All right, so we can see that the resultant force is going to be 2 times T, because you're going to have this, both of these, this T and that T, both of them are going to be resolved into the angle. So it's times the cosine of 18.435. So the resultant force is going to be 2 times, now T is 2 over 3 times 9.8 times the cosine of 18.435, and that should give us our answer. So we have 4 over 3. So let me take the cosine of that first. Cosine of the answer, okay, and that's going to be multiplied by 4 over 3 times 9.8. 4 over 3 times 9.8, which gives you 12.396 12.396 newtons, which we should round either to 2SF or to 3SF. So if you write it as 12 newtons, that's fine. If you write it as 12.4 newtons, that's also fine. Okay, so that's by far the simplest way of dealing with the question. There is another way of dealing with it if you think about drawing the triangle of forces, which will work. So you've got, say, the tension acting in this. Let me use these arrows. Solid line. Okay, so you got the tension. What's happened here? So you got tension acting in this direction, and then you got the tension acting straight down. They're both equal in length, and the reaction force is where you join the resultant force is where you join the beginning to the end. So this is the tension in one string, this is the tension in the other string. Okay, and this is the resultant force. So we know what this is, we know what this is. If we find this angle, we can find what R is. Okay, this is I guess a longer way, but maybe more understandable. So basically we need to find what this angle is. Now this angle is basically, if we continue this line along, let me do it in a different type of line. Okay, so but if we if we carry on this line here, that angle here is the same as the angle we found, which was double this 18.435. Okay, this angle here, okay, this angle here is basically 90 minus our alpha. Okay, 90 minus 53.1. So this is 90 minus 53.1, this angle. Okay, so I'll just show you how to do it this way and see if it should give you the same answer, just in case you prefer this way. So you have here 90 minus 53.1, 90 minus 53.1. I've lost my accuracy now, but just for purposes of showing you, that's 36.9. So the angle we need is 180 minus the angle. So it's 180 minus the 36.9, which gives you 143.1. 143.1. And we can now use a cosine. We can say R squared equals, you're going to have T squared plus T squared. We know what T is, it's 2/3 G, minus 2 times T times T. So it's 2T squared times the cosine of 143.1. So let's see if that actually works. So we're going to have basically T squared plus T squared. So remember, T is 2 over 3, 2 over 3 times 9.8. Okay, 98 over 15. Okay, so what I'm going to do is this. I will store this as A, and then I'll use that. I'll say, okay, I'll have 2 times, that's A squared, minus, whoops, 2 times A squared, minus 2 times A squared, okay, times cosine 143.1. Okay, and then I find the square root of that. And yeah, it gives me exactly the same answer, 12.395. So R equals 12.395. This gave me a slightly different answer. Why? Because I had this angle. I didn't use the exact value for it. So, I mean, it's fine because the answer, when we round it, is either 12 or 12.4 newtons. So these are two different ways I've shown you how to do this. This is probably easier in terms of actually doing it, but maybe not so much in terms of understanding the concept, but it's to do with resolving forces, and when you resolve them like at perpendicular and parallel. Okay, so I'm resolving this force parallel to the resultant force. Okay, so it's going into the angle, so you're going to use cosine. So for this, it's t times cosine of that angle, because the angle that you're going into is a half of that whole angle, which is 90 minus alpha. So it's t times cosine of 18.435, and then from this side as well, t times, as you're going into the angle, the same thing, 18 times cosine of 18.435, so you end up with 2 times t cosine 18.435. And the other way is to draw a triangle of forces, draw this force, draw that force, and then the resultant is from the beginning to the end, from where you started to where you ended, and you have to just try and figure out what that angle is there, and you can use the cosine rule, and it gave us the same answer. Okay, thank you for watching.